Hey guys, this is Mrs. Harmon, and we are in Chapter 4, which is all about Mrs. Harmon, and we are in Chapter 4, which is all about inequalities. And we have looked at graphing inequalities, and then we solved inequalities for a variable, looking at the properties of inequalities. Today we're going to look at a special type of inequality, and we're going to look at conjunctions. Conjunctions. Now this is a word that you should be familiar with, that you've probably heard in English before. We know in English when we talk about conjunctions, we're talking about those words like and, or, but, while. Those are words that join two clauses or two ideas together. Well, that word conjunction has a similar meaning in math, and we're going to take a look at how we apply that to inequalities. Our lesson objective for today is this. You, the student, will define, solve, and graph conjunctions. Now, when we look at compound sentences in English, we know compound sentences are joined, or two sentences joined with the word and, but, or, nor, so forth and so on. In mathematics, a compound sentence is made by connecting two statements or two expressions using the word and with a word or. And we're going to look specifically at conjunctions today, which deal with just this word, and. So conjunction is a compound sentence, compound math sentence, consisting of mathematical statements connected by the word and. That's what you need to remember. Connected by the word and. Con, if we're looking at roots, con means with. So we're going to look at two different sets of inequalities, and we want to know which numbers are in both one and in the other. Which numbers, which solutions are in both one and the other. Let's take a look at what that looks like in some math problems. I think it'll make a little bit more sense when you see it with some numbers. The important thing to remember before we get started is because we're talking about conjunctions and we're looking at the word and, a conjunction can only be true where both parts are true. So conjunction is true if it's true for one and it's true for the other. It has to be true for both. Both and go together. So let's take a look. We have two different inequalities, and we want to graph the solution set. We want to graph the conjunction of these two. Which solutions are in both this inequality and this inequality? Remember, both and go together. So this is a conjunction. And in order to do this, we're going to graph the first inequality above the number line. We're going to kind of eyeball where it should be there. Then we're going to graph the second inequality above the number line. And the two places where they overlap or have solutions in both of those inequalities, that's going to be our final solution set. So let's take a look at what this looks like. X is greater than or equal to -1. Looks like this. We've got an open circle because it's not equal to -1. It's just greater than. And our arrow goes to the right because greater than has the R in it. Greater than goes to the right. X is less than or equal to X is less than or equal to 4. Looks like this. A solid circle at 4 because we've got this equal to part. And then less than goes to the left. So our arrow goes to the left. And when we look at those two, if we could move these one on top of the other, you can see that these two lines do overlap. They overlap here through here. All of these values are in both of those inequalities. Remember, a conjunction, we want to know which values are in both this one and that one. So our solution set is going to show us all the values that are in both of those inequalities. And so in both of those inequalities, we're between here and here. We know that X has to be greater than -1 or less than or equal to 4. Because we've got a solid circle here and a solid line, we can include that less than or equal to 4. Because we've got an open circle here, we do need an open circle in our final solution set. So this is our conjunction. This is the All right, my microphone cut out there, so I'm not sure exactly where it stopped working. But just remember, a conjunction shows us which solutions, which numbers are in both one and the other. Now let's take a look at another one. We've got X is greater than -1 or less than or equal to -4. -1 is less than X, which is less than or equal to 4. That was the solution that we just found to example 1. A lot of times you'll see this symbol. This symbol is often used for the word and. It kind of looks like maybe a lowercase n, so that can help you remember that that symbol means in, like an and. Okay? Or like a capital A, like an and. Whatever will help you remember that. So let's graph and state the solution to x is greater than or equal to 5 and x is less than 0. So again, we want to graph both of these inequalities individually, and then we want to tell which numbers are in both one and the other. So when we graph x is greater than or equal to 5, you can see solid dot at the 5 and our arrow to the right, and x is less than 0, open circle and going to the left. And where do these two graphs intersect? What numbers are in both of those lines? Well, hopefully you said they don't intersect. There are no numbers that are solutions to both, and in that case our answer is this empty set, this null sign here. There are no points in the solution set. There is no conjunction, no place where they overlap, no numbers that are in both of these inequalities that would make both of these inequalities true. Let's solve and graph the solution set now of two longer inequalities. 2x plus 5 is less than or equal to 11, and negative 3x is greater than 18. The first thing we need to do is use our properties of addition and multiplication to solve for our variable there. So we're going to solve the one on the left to get x is less than or equal to 3. And then we'll solve the one on the right to get x is less than negative 6. Now if you're wondering why or how the sign changed, don't forget, when you multiply or divide both sides by a negative, you've got to switch that sign. Let's go ahead and graph those on a number line and see where our conjunction is. On a number line, x is less than or equal to 3, it looks like this, and x is less than negative 6, looks like this. Right, so where do we intersect? Well, you can see from here, moving on to infinity there, we've got a point of intersection. So our solution set is that x is less than negative 6. All values of less than negative 6 would be part of both of these inequalities, making both of those inequalities true. Let's take a look at a combined conjunction. Okay, we've got 3x plus 5 in the middle, and this combined conjunction shows us that 3x plus 5 is greater than negative 1, and it's less than 8. So what we want to do is separate those into two inequalities, separated by the word and, because we're looking at conjunctions, and then again go about solving those two inequalities separately, graphing them and looking for the conjunction. So let's separate that. We've got negative 1 is less than 3x plus 5, and 3x plus 5 is less than 8. We'll then work to solve our variable here. Now, we could solve it all together. We could subtract 5 from here, and whatever we do to one side, we have to do to the other. But that can get a little confusing, so it's easier just to go ahead and break it into two inequalities and solve this separately. Let's go back. We didn't finish solving that one. If we were to go ahead and solve this one, we would subtract 5 from both sides here, and again subtract 5 from both sides here, and then solve for that x and find that point of intersection. This one is worked out for you in the book. I'll try to get it worked out here on the screen. I may run out of room here. But we get negative 6 is less than 3x, dividing both sides by 3, positive 3. We get negative 2 is less than x. We don't have to switch the sign because I did not divide by a negative. Negative 2 is less than x. And over here, we've got 3x is less than 3. Divide both sides by 3, and I've got x is less than 1. Okay, on a graph, then what I get is that, this is negative 2 here, x is greater than negative 2, x is less than 1. So our solution set is that x is greater than negative 2, but less than 1. So there is that final answer. Hard to fit all that in the screen. Hopefully you can see it. In the previous example, both of the inequalities required that same step to solve. We don't always require the same steps when we're solving inequalities. So sometimes there are different steps required, and then in that case, inequalities must be written separately. I would suggest that you write them separately or split them into two inequalities every time. It's just so much easier. Let's take a look at this example. X minus 3 is less than or equal to, 2x minus 9, which is less than 15. Let's go ahead and break those into two inequalities. Here's our first one, and here's our second one. So we get x minus 3 is less than or equal to 2x plus 2x minus 9, and 2x minus 9 is less than 15. We'll solve for x, and both of those, we get x is greater than or equal to 6 on the left, and on the right, we get x is less than 12. If we were to graph those, we would find out that our solution set is that x must be greater than or equal to 6 and less than 12. On a number line, that would look like this. Let's just put a 6 and a 12 here randomly. X is greater than or equal to 6, so solid dot here going to the right. And it's less than 12, so open dot going to the left. So there is our solution set on the number line. Today we defined, solved, and graphed conjunctions. Remember that a conjunction is going to use the word and, which is represented with this symbol. And it's telling us which solutions are, or which numbers are solutions to both inequalities. Which one is in both this one and that one. So very important that you remember and means both. Which solutions are in both. If you didn't write that down in your notes, make sure you get that written down. That is super important. If you have any questions, be sure to ask me next class.